Hello everyone, I'm gonna solve the 77th problem firstly. So here the capacitor in the figure are charged and the switch closed at t equals to 0 seconds, and at what time has the current in the 8 ohm resistor decayed to half the value it had immediately after the switch was closed. So firstly, I'm just gonna write the given. So yeah, after which I will solve the problem. Yeah, and as I noticed, our goal is to find the time at which the current in the 8 ohm resistor reached half of its initial value. So yeah, and we have the certain formula for that, as we all know probably. That's called I equals to half of I initial, I0. So firstly I have to just write the capacitor, exactly the series one. Here we have the series capacitor in a row, so I'm just gonna multiply plus them vice versa. So I'm multiplying 60 and dividing by 112 20. So yeah, that's equals to 30 microfarads. Oops, I just wrote the Russian farad. Let me just correct it, fix it. So now I have to find the combination in parallel capacitors. So I'm just gonna plus the 30 microfarads to 20 microfarads. They are parallel, and that's gonna be 50 microfarads. Really easy. And then, of course, to finish our equation, I have to find the equivalent of resistance. So now I'm gonna just multiply 30 and 20 ohms by dividing 50 ohms as a capacitor. I'm adding them by vice versa way, so that's going to be 12 ohms. Really easy as well. So this block is the series with the A capacitor resistor. So let me highlight it firstly. Yeah, I'm highlighting, and then yeah, so I have to add the resistors equally, like that is really easy. So I just have to add them by their current numbers. So 8 plus 12 is equals to 20 ohms also. So we're at the finish. So let's solve the time here. So the discharge current follows the equation like as I said before. So I equals to I0 multiplied by electron, like in a index here we have negative T divided by torque. And here we can just find the torque is R, exactly resistor multiplied by capacitor. So I'm just multiplying the capacitor by capacitor, of course. So it equals to 12 multiplied by 50 microfarads. So yeah, and totally it equals to 100 microseconds. Yeah, we can just write it as a 1 millisecond. Let's write it here. Yeah, so I just gonna write the 0.5 as I highlighted before. So is it equals to electron in an index is negative time divided by torque. So here we just have to find the time by like make it logarithm. So I just have to write the ln to both sides. So ln is logarithm e, and electron e is gonna empty here, not electron and e. So here I just will find the time by multiplying the torque to ln 2. yeah, so yeah, that's easy. At the final, so t is equals to exactly time equals to 1 milliseconds multiplied by approximately, that is equals to 0 893. I just calculated it before, so yeah, we just have to write the millisecond here. So let me highlight it. Yeah, that's it. That's totally right. Let me write it here as well. So here is my second problem, sea level problem. So the switch is in the figure has been closed for a very long time. So first unknown is what is the charge on the capacitor. The second unknown is the switch is opened at t equals 0 second. At what time has the charge on the capacitor decreased to 10% of its initial value? So let's write the firstly. We have to find the voltage across the 40 ohms resistor. So I just multiplying the 100 volts, and in a brackets are 40 ohms is divided by 100 volts as well, so it is equals to 40 volts. I think is really easy. So then, since no current flows through the 10 ohms resistor, the voltage across the capacitor is the same as the voltage across the 40 ohms resistor. So I'm gonna write the VC is equals to 40 volts. So yeah, and then I have to find the initial charge Q0. So Q0 is equals to, like, the formula is capacitor multiplied by V is equals to 2 microfarads is multiplied by 40 volts, and that equals to 80 micro coulombs. Yeah, so let me just write it immediately here. Yeah. So then we have to find the discharge resistance. So that is equals to 10 ohms plus 40 ohms is equals to 50 ohms. Yeah, those are in a row. So, and discharge time constant also we have to find is equals to discharge resistance multiplied by capacitor is equals to 50 ohms multiplied by 2 microfarads. And that's approximately 100 microseconds. Yeah, I guess. Yeah, exactly. And so solve for t exactly time when q is equals to 10% of q0. So let me write it here. 10% is 0.1 equals to q0. So yeah, so like the formula before I'm writing here. So let's find it by ln as well, and by negative t divided by torque is like here. Easily we can find the time. So time equals to, as I wrote before, negative torque multiplied by ln 0 1. So just I'm gonna send the negative minus to the index of 0 1. Let me write it here to show you. Yeah, so and by minus 1 index, that's gonna just be vice versa and become 10. So t is equals to approximately 100 microseconds multiplied by 2.3 is approximately equals to 230 microseconds. That's it. So let me highlight it as well here by yellow colors. Yeah, and that's it. Firstly, I simplified the circuit to find the total values. Exactly, capacitance, as I mentioned it before in equations, the total capacitor is 50 microfarads. What about resistance? Resistance is 20 ohms. So next I calculated the time constant, exactly tau, multiplying R and C, exactly resistant capacitor as it constant it gives 1 millisecond, finally finding the time when we need to know when the current drops to 50% in a RC circuit. This happens at t equals to tau multiplied by ln2. So since ln2 is approximately 0.7, the final answer is 0.7 milliseconds. So as you can see in my Felsted simulation, the graph confirms the exponential decay perfectly. Thanks.